Alright, thanks for coming back again. The topic now is placing electrons into energy level diagrams or energy orbitals of various energies. You probably know this, don't you? That the 1s orbital is the closest to the nucleus, followed by the 2s orbital, followed by the 2p orbitals, and followed by the 3s orbital. They're a little bit discontinuous up here as I get to the 4s, a little bit lower than 3d, but we can look at the periodic table in a second to rationalize that. Arrows represent electrons, so this is a spin-up electron, and this is a spin-down electron, and that's, wow, a pair of electrons. What do you know? One spins up, one spins down. They never can be two electrons in the same orbital, spinning the same way, so to speak. The m sub s spin quantum number has to be plus 1/2 and minus 1/2 for another one. The Pauli exclusion principle says you can't have two electrons in the same orbital doing exactly the same thing. So for example, when I put my first electron in the first orbital, it goes something like that. I call it usually a spin up. It doesn't matter, you could draw it down if you want to, but the convention is usually it's drawn up. And that would be the energy level diagram for hydrogen, because it only has one electron. But if I put another one in, it builds right here. What is that rule? Oh dang, I'm having a mental blank. Hund's rule, I think it is. You fill up the orbitals from lowest to highest, and you fill them up before you you fill that orbital up before you go up any higher. So the ground state for helium looks just like this. One spin up, one spin down, and the electron configuration is 1s2. I would stop right there in my writing of the notation. But if I want to continue, oh yeah, this is called the Aufbau Principle, correct? Yeah, building up from the smallest to the biggest atom. So hydrogen and helium, and this is lithium. Lithium has a 2s1 electron. Then the next electron, wow, are you surprised? It's going to go right here. You're probably not surprised. Where would the next electron go? Oh, well, it needs to go up a little bit higher in energy in the 2p orbitals. Yeah, so what's that? Boron. Yeah, boron. Yeah, 2p1. So if I wrote 1s2, 2s2, 2p1, that would represent the boron. But if I continue building larger and larger atoms, more and more electrons, this next electron, that would represent carbon. Yeah. Oh yeah, and this is the, again, Hund's rule. I spread these out in these energy levels. The 2px and the 2py and the 2pz are equivalent in energy. They're called degenerate orbitals. So if I'm placing 1, 2, 3 electrons in those three orbitals, they will spread out because electrons are negative and they want to get away from each other as much as possible. So this would be called the 1s2, 2s2, 2p3 element, and of course that's nitrogen. Huh, interesting. Now I can go back and fill that those orbitals up with another electron. Usually it's drawn here, but honestly I could have put it here or here. It doesn't really matter. That would be oxygen. Yeah. And that's why, in other words, 1s2, 2s2, 2p4, 2p4, the 2p4 element is oxygen. Placing another proton in the nucleus, therefore another electron, would look like this. And wouldn't that be fluorine? Yeah, it is fluorine. 1s2, 2s2, 2p5, or lastly, to fill up this little shell, second principle quantum layer, looks like that. So that's the 1s is full and layer 2 is full. And oh yeah, so if this is helium, this noble gas would be neon. Yeah. Where'd the next electron go? Oh my goodness, are you getting bored of this already? My next electron goes here. That's the 3s1 element. Is that sodium? That's sodium, the 3s1 element. I keep peeking over my shoulder at the periodic table. I don't have this quite memorized yet. I don't expect you to either. And that's a 3s2 element. That's magnesium. Magnesium would be 1s2, 2s2, 2p6, 3s2. The next electron goes, and then, Usually they're all drawn up like this. Actually, if you look at, let's see, let me do this one for the 3p. What is the 3p3 element? Oh, it's phosphorus. So if I were looking at phosphorus electrons in the ground state, they actually do spin all in about the same direction. Not about, totally. It's actually a lower energy configuration to have it be like that, as opposed to having one up and one down. Sounds kind of silly, but indeed, that's the story. Now, if I were to go beyond phosphorus, so that's 1, 2, 3, 4, 2, 4, 6, 8, 10, 12, 13, 14, 15. Yeah, element 15 is phosphorus. Element 16 with one more proton in the nucleus and one more electron. The electron must fill into an orbital like that. Sulfur and chlorine. One electron shy of an octet. Oh, we haven't defined octet yet, have we? Oops, I don't want that one. That would violate Pauli's exclusion principle. I can't put two up arrows in the same orbital. There we go. That's better. And that looks like 1s2, 2s2, 2p6, 3s2, 3p6. And indeed, that's the next noble gas, argon. Well, let me just do maybe one more. How do you like that? That's potassium, is that right? 4s1 element, potassium. And then the next element, calcium. And then the next electron, whoa. So I'm going from bottom up. You don't have to remember these in this. I wouldn't remember these orbitals in this order from this pattern, but I would remember the orbitals in the next pattern that I'm going to show you. It matches with this one, but it's easier to remember. So what is that? It says 3d5, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5, and I believe that's manganese, Mn. If I were to place iron, electrons for iron, element 26, 26 protons and 26 electrons, right about there. Interesting. So often we'll talk about unpaired electrons. It looks like iron in its ground state has 4 unpaired electrons. That actually means something about magnetism, but in any case. Oh, look at this. Another way, as you probably recognize, is that if this is helium, this is neon, this is argon. If I wanted to, I could write my notation abbreviated with the noble gases in square brackets. And indeed, also, sometimes we'll ignore writing the 1s orbital if I'm just talking about the valence orbitals of 2s and 2p, or if I was talking about the layer 3, like say it's 3p, sulfur, phosphorus, chlorine, or something like that. They might not even give these lower inner core orbitals. They might just give this one as a picture and this one as a picture and say fill in these two from there. So yeah, noble gases. I also bothered to put some description of the quantum numbers here. That might confuse you, but it's a good connection to try to struggle with. And lastly, look at this one. This is hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, chlorine. Oh wait, nitrogen, oxygen, fluorine, and neon. And again, that goes 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, and remember those will be spread out amongst the 2px, 2py, and 2pz orbitals. Then this will go back and pair up in the 2px and the 2py and the 2pz, or I could call this the 2p1, 2p2, 2p3, 2p4, 2p5, 2p6 element. Then I go 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, tongue twister. Then 4s1, 4s2, 3d1, 3d2, 3d3, 3d4, 3d5, etc., etc. Interesting. I would actually try to remember this. I know this is the S block, I know this is the P block, I know this is the D block. And then this is 1s and 2s and 3s. A little discontinuity here. But if you can remember up to this spot, up to this n equals 4 line, which also includes some, the d orbitals there, that would be a really good thing to think about, study, lose some sleep over. Alright guys, thanks. I'll catch you in lecture discussion. Thanks for watching.